Welcome to my introduction to programming. And I'm having this talk because I think programming is awesome. Actually, I think I think programming is awesome, and I think more people should do it. And so I want to talk about what programming is and what we're doing so that people can think, is this something I want to do? Is this something that sounds exciting? And so, yeah. So, who am I? I am Liam. I'm a programmer. I also have the nick on the IRC that nobody can pronounce, and I don't have a demo group yet. I am also a web developer for the backend of a computer parties management system. I'm a software developer at Fuse, and I'm a local crew here at the gathering. So, why am I here today? Well, as I said, I think programming is awesome. More people should do it. And I know it can be hard to get started, and it can be hard to decide, if you want to do this or not, because it takes a lot of time, and most people don't have time in their life to learn programming. But I really recommend this as something to do. So, what is programming? Basically, now that picture is very dark, but basically we're writing instructions for the computer to execute, which basically means we're doing stuff with numbers, and it's nothing more to it. It's as complicated as you want to make it yourself, meaning, you don't have to do rocket science, or you don't have to make the next demo that wins a competition at the gathering. It can be as simple as, writing an IRC bot, something I know a lot of people who do programming do. It's a bit hard to see this comic, but it's from XKCD, and it's I think it's a good representation of how programming is on a low level. So what can you do with programming? A lot more than you think. A lot of people, when they think programming, they think, apps, games, and stuff like that. But that's only the beginning, and that's only the more popular subjects. And you can find a lot of more interesting things to code if you just, if you have an interest and you find something that you need to get done in that interest. It's a it's a problem-solving tool, basically. So, anything you need to do, you can probably apply programming to it in some way, automate it, do statistics on it, anything. And that's why I think it's cool. So, how does it work? On a simple level, all we do is write a list of instructions that the computer runs one after each other. We can either do something to a number, like add something or subtract something, or we can compare two numbers. We can move numbers around the memory, and we can jump to somewhere in the program. So let's say, if a player's health is less than 0, jump to game over screen, or something like that. It does sound like a lot of work, but that's what we have abstractions for. Modern programming languages normally don't do a lot of that stuff. It's normally done for you, and you are given a more user-friendly way of talking to the computer. So I thought I'd show a quick demonstration in Scratch of what programming is, because it's a really nice language for learning basic concepts of programming. It's written and hosted by MIT, and we've been using it in school. And I think it's a nice way of, getting to learn programming and getting to learn how to write functions. So, if we open Scratch, here. If you want to try this out yourself, you can get it at scratch.mit.edu. I'll just have to duplicate. Yeah. It's a scratch.mit.edu. And in Scratch, you have sprites, or figurer as they're called in Norwegian. This is the Norwegian version of Scratch. that you can use blocks that look like this in order to do stuff. Sadly, I didn't know how to put it in English, and since we're in Norway, it just defaulted to Norwegian. But for English viewers, just hang on, because I'll explain this. So in Scratch, we have this window here, which shows our scene, and it's basically a blank canvas on which what we program happens. We have this list of sprites or objects in our scene, and we have different things we can do. We can change how they look, and we can add sounds. But for now, I thought I'd show a simple particle effect to just demonstrate how we would write a function. So we would start normally by writing a function that's called when the program starts. It's where the program starts. And in Scratch, it's when this green flag is clicked. So we say when the green flag is clicked, we want to create multiple of these, and we want them to fall down randomly so they look like particles. For that, we'll create the function. And I'll just do that now. You don't need functions, but I'm going to do it to make things easier so that you can understand functions at the same time. So we'll make a new function called create particle. And what's going to happen is when we run create particle, blocks we put on here are going to be run. So if I go under control and drag out the forever loop, which will run the contents of here forever, we can then add the create particle block here in order to run this. So this is going to loop forever and run this function. And so in this function, we can get one of these. Let's see, where's this? That's probably, yeah, here. So in create particle, we're going to tell Scratch to create a clone of me. And because we have this selected, this is what we're going to create a clone of. Though if we run the program, nothing is going to happen. This is because, yeah, it is making a clone of it, but on top of itself, so you're not actually going to see any change. So what we do instead is we add a new event that's going to be run when this is created as a clone, which is here. I'm going to go through the program once I'm done programming it and talk through how it works as well. So if this is created as a clone, we want to create two values for this object. We want to create the x direction value. We don't actually need another value, so that's fine. So what's going to happen is we set x direction to some random number between, let's say, -5 and 5. Now, this line is now telling Scratch that we want to remember a value called x direction, and we want the value of x direction to be something random from -5 to 5. So from then on, we can do, for example, we can repeat 30 times. Change x and y. What this will do is 30 times we'll run these two blocks, which will change the position of the ball on the screen. We want to change y by, let's say, -1 per repetition, and x by x direction per repetition. Actually, say -3 to 3, just. And then afterwards, when it's done repeating that 30 times, we don't want it to be on screen, because that's going to lag. And also Scratch stops you from creating more after about 200. So what we're going to tell it at last is, when we're done repeating these two commands 30 times, we're going to delete the clone, which basically says goodbye to it, and we have space for more. And so if we run it now, we'll see some particles, and they're not moving really fast, but if we say move by -4 each frame or each repetition, it's going to move a lot faster. And this might not seem like much, and it looks like a pretty boring effect, but this is the basics of how most particle effects are actually made. So, you know, the smoke you see in video games, stuff like that, is all basically this. So, to sum it up, what we've actually done here is when the flag is clicked or when the program starts, we're for always going to create a particle by running this function, which we are telling Scratch about here. And we're telling Scratch that create particle is supposed to create a clone of itself, which is our sprite. All this code runs on this sprite. When it starts as a sprite, it will remember for itself a value we call x direction, which is the direction in this axis that we want this to move. And we'll make it set the value of this to something random between -3 and 3, which will make it vary randomly between going to the left and going to the right. Afterwards, we're going to 30 times move the dot. We're going to change x by the value we remembered earlier, because if we move this here instead, we're going to see that it moves randomly and it can change direction. So instead of that effect, because we wanted to go in one direction, we have to remember the random number between each time. And then when it's done, it deletes itself, so we have space for more. No, if you change the amount of times we loop, they will survive for longer, and you'll get a more fancy effect. And then of course, if you tweak these parameters, you'll get a wider spray of particles. And so this is the basics of how particle effects work. And I think this is a really nice example to explain basically what programming is about nowadays, because most of the complicated stuff that I talked about earlier with moving stuff around in memory, we don't do that anymore normally. Instead, we have simple things like this, simple logic like this that's a lot easier to follow. There is some things today and some cases today where we want to move stuff around in memory, but that would be if we, for example, are working on a platform that's very slow, so we don't have the extra processor power to let a program handle stuff for us. And so on some platforms, like for example Arduino, we need to be able to have complete control over what's running. But for a beginner, especially if you're not going to learn programming on a slow platform, I would recommend this. There's also 4K programs, 4K demos that we have had earlier on the gathering, where basically some artists write a program in 4 kilobytes that shows a visual effect. It's really impressive, where you would have to actually have control over it yourself, because those 4 kilobytes, you use them up very quickly, so you need direct access over what each byte is actually doing to the computer. And so then, the program gets a bit more complicated, but we're not going to care about that, because that's complicated. So, that's right. Extend. Sorry for that. Thank you. Okay, so let's now sum up what we've done. We've made a particle that emits more particles. We can animate them using maths. In our case, we animated them to move downwards at the angle. We can loop in order to move it multiple times and therefore create the visual effect of it actually moving, because it's not actually moving, we're just doing small increments. And we can also run pre-made instructions to complete those tasks. So as you remember, we did define a method or a function that created the particle, and that's an example of that. And that's really nice, because then you can reuse code. So, you know, sounds easy. I mean, yeah, it's a bit complicated when you first start off, but once you get the hang of it, it's really a simple thing. And it just clicks. But it gets better. And this is where the exciting stuff comes. There's not always just one way to solve something. With maths, well, actually with complicated maths, you will get more ways of solving something. But not all given problems have an optimal way of solving them. Like, for example, an AI. There is not always one optimal way to write the AI. There's not always one optimal way to actually make it. And so you will have different AIs from person to person who work and think differently, but do the same task. Also, sometimes you need to optimize. You can write really slow and sloppy code that does what you want it to do, but is slow. But in some cases, like in real-time graphics, like in a video game, you will actually have to make code that not only runs, but runs fast. And so, you know, that's another challenge. And also, human mistake always gives room for fun errors that take hours to debug. So I thought I'd use the last part of the presentation to talk about some different examples of popular ways we have tried to solve problems that we don't always have clear solutions for. So the first thing I thought I'd talk about is A*. And it may not sound like something, but it's an algorithm for pathfinding. And what that means is that it's a set of instructions we have found for finding our way around somewhere, for finding a path. It's very popular. I've seen it a lot in AIs written at the gathering, and it's very easy to implement. And so basically how it works is, while we have not searched all, it works by dividing a map into grids. And a grid is even possible to walk through or not. And it works by saying that while we have not searched all grids or we haven't reached goal, we're going to store the number of steps it takes to reach that grid in each neighbor tile and repeat the process. So let's say we have this maze, right? How do you get there fastest? Well, of course, you walk around here, down here, and up here. But how do you tell a computer how you do that? Well, that's what A* is an attempt at doing. So how A* works is we're basically, for each tile, setting a number for how many steps it takes to reach that tile from start. This is 1 step, 2 steps, and you see how it works. Here they intersect, but this is shorter, so this is the dominant path that actually is allowed to go up and go here, while this just cuts off. Then what we do is we start at the end, and we see, okay, which of the neighbor squares have the lowest number. And in this case, there's only one neighbor square, and the number is 29, so we'll have to go there. And we'll go along here. And here is one of the examples where, you know, you actually have to make a decision of where to go. When the computer is at this square, it thinks, okay, I have 2 neighbors I can walk to, 21 and 19. Well, 19 is the lowest, so I'll walk to 19. And you know, that's how it works. And it gets back to goal, and when it's back at goal, it remembers where it walked, and that's the path we're going. Just wait for man in the roof to be done.
Those of you who need chairs, find those on both sides of the stage. Och deras som har köpt hyllor kan man hämta hyllorna föran scenen.
Okay.
Those who have purchased shelves can pick up your shelf in front of the stage.
Okay. Another example is sorting, which, you know, we already kind of have a algorithm for in your head. You know, if you are to sort 10 numbers, you have a way in your head of doing it, and it's quite similar to how a computer does it. So I thought I'd show a video, or a bit of a video some guy did, where he's basically visualizing how some sorting algorithms work, and there's sound too, and so you can actually hear how it sounds as it's working. No, I'm not going to show much of it because it's 5 minutes long, but I think it's a nice example of how sorting works, and it's entertaining enough. Now, this might be a bit loud, so I'll just... So, here you can see how different sorting algorithms work. This is selection sort. This is insertion sort, where it goes to the right, for each column finds its spot in there, and then just inserts it. So you can kind of see how it is thinking. And you know, these seem quite straightforward, but there's people competing in how to write the fastest way of sorting stuff. And so, you know, there's a lot of stuff about that. Here's quick sort. It divides, and then it sorts based on height. So you can see this is highest part, lowest part, and it sorts like this. Also very noisy. And the last algorithm I'll show is merge sort. Yeah. This is a fun one where it takes parts and then merges them together like this, and then again, and then you kind of get, yeah, you know, a sorted set of numbers. So yeah, that's sorting. Oh, okay. Okay. So the next thing is AIs, which I think is something cool, because there's a lot of there's a competition at the gathering where you have to write an AI, and it's very challenging, but really fun if you manage to do it properly. This is a really fun one because if someone was to ask me, you know, Liam, what's a good example of a task where there's a lot of different ways to solve it, I would say AI. Today, no, this year's task is writing a bot that drives around a 2D Mario Kart round, and you're supposed to complete it in as slow time as possible, and of course, you know, your enemies can shoot blue shells at you and stuff like that. And so people have made ways of solving this problem and making an AI that can drive around in a lot of different ways. There's a lot of vector maths, and there's a lot of prioritizing code, and, you know, stuff like that. But another thing is neural networks, which is a kind of AI you can write, where you basically have a bunch of nodes, and each node can take in some numbers, and it's connected to other nodes. And the node can vary how much of each input number it wants to care about, and the node does a simple mathematical operation. So one node may add a few numbers, one node may multiply some numbers, and, you know, that might sound like much, but apparently I was told by Martin, Google Voice and some other voice recognition programs use neural networks in order to understand speak, because if you do not know how to fix the problem, neural networks is a thing you can throw at the problem, and you vary variables and you vary the input, and after a while you'll get a neural network that will try to solve your problem. And so it's basically trying to simulate what's happening in your head, which is cool. But normally AIs, especially here, is just the combination of different algorithms like pathfinding and prioritizing, where you have different options and then the AI has to decide which of the options it needs to do the most. So that's cool. Last year there was a Bomberman AI competition. There was some good AIs there. So that's cool, but where do I go from here? I mean, you've not taught me any programming. Well, if you think programming sounds cool, and it is cool, start learning a programming language. A few good ones that I would recommend is C#, Java, JavaScript, or Python. Some people are probably going to jump at me for saying Java, but if you play a video game that supports modding like Minecraft or Garry's Mod, you could learn the programming language you use for the modifying, and you can write mods for the game you play. So suddenly it's not just boring programming, you're making an extra gun in Garry's Mod, or you're making the next modification that becomes big in Minecraft or something like that. And that makes it a lot more fun, especially for learning the basics, because learning the basics is by far the most boring part of programming, because it just takes time and you have to understand it, and also you have to kind of get a natural feeling for how it works. Another thing I would recommend is ask a mentor, because we have mentors here in programming. They sit there and they are here to help you. Just ask them, don't be shy. I mean, they're nice people. And yeah, also we have IRC. Creativia at fnet.net or something like that, or I use homelien.no. You can ask there. There's people there who might be able to answer your question. If not, Google is your friend, because in the end, there's a lot of stuff you learn from Google and websites like Stack Overflow. Even if you're a beginner, you can probably just Google your problem, and Stack Overflow or something else on Google will have your answer. The hardest thing about that is you will not always know how to describe your problem, but that's something you learn. So in the end, it's just to get to it, because the faster you can complete, learning the actual language and learning how to speak your programming language, the faster you can start doing, actual programs that do something awesome. And I mean, there's tons of cool stuff you can do with programming. You just need to have some creativity in order to, come up with stuff. Maybe it's something at home you want automated, or maybe you found some website and you want to get some data from that. You can do data mining, and as I said, modifications for a game is a big thing. If you play World of Warcraft, for example, there's also a Lua library for that, so you can write add-ons. There's also, you can write bots, which is AI, for example, our AI competitions here. And it's all cool stuff. And probably after a while, you'll get good at it, and you'll be able to say, okay, I've written some cool stuff, and you can come here and be a part of our competitions, and maybe even give a talk sometime in the future. Who knows? But the most important thing is that you start, because the more you wait, the longer it will take before you actually start programming. And you only learn so and so much from actually learning. Most of it is just programming and just time you've spent on your computer programming. It's all about experience. So yeah, that's it. Hopefully this has given a nice insight to what programming is on a basic level, what kind of things we do, how we think, and what kind of problems and trouble you might run into that you'll have to learn to fix. So yeah, that's it. If there's any questions, you can ask me afterwards. And as I said, go say hi to the mentors. And yeah.